Well, welcome everyone to the Alleviate Injection Molding Issues webinar today. We're going to be talking about SolidWorks plastics, obviously. Hope that's what you're all here for. My name is Jared Spaniel. I'm one of the product managers at Digital Dimensions, and I am out of the Fresno office. You can see my contact information there on the screen, jspaniel@ddicad.com, and I will put that up again at the end if you have any lingering questions or anything that you need to contact me about regarding this webinar or our products. So what are our goals today? I have a few goals I'd like to accomplish here and what we're going to actually look at. Hopefully we'll be accomplishing all of these. First one, we're going to set up a study in SolidWorks Plastics. I'm going to briefly show you all how to do that. Next one, we're going to analyze some injection molded parts for defects, which is why I hope you're all here and basically the gist of what SolidWorks Plastics does. Next one, good one, using configurations to evaluate our designs. I'm going to show you how to do that. I've got a few configurations pre-set up that we're going to look at. Next one, make critical design changes to reduce molding issues, which is another huge concern and another great thing that's the SolidWorks Plastics or any of our simulation softwares allow us to basically do. Figure out what's exactly happening and what design changes we need to make to reduce our issues. So a brief overview of how I structured this. We're going to look at just generally what is SolidWorks Plastics for those of you who might not know. Who is it for? Who's this benefit? What are the main people that might use this software? And then we're going to look at SolidWorks Plastics in the actual software itself, go through a few things, and then why would you want to use SolidWorks Plastics? What are the main benefits of this software? So first thing I wanted to do was kind of release this poll question and get a feel for who the audience is or who we have in the audience today. So what are you currently using to simulate your injection molded parts? I'm going to go ahead and launch this question right now. Appreciate everyone. Just go ahead and answer that. The choices are SolidWorks Plastics, MoldFlow, another 3D plastic sim software, or we just don't use simulation at this time. And I'll give another moment here to let some more votes come in. And then I will go ahead and close this out. All right, I'll close this out and for time's sake. Let's get moving on here. So it looks like most people don't actually use any simulation software at this time, which that's fine. That's what we're here to learn about. That's what we're here to explore. So great, let's check this out then. So I know who my audience is. So the first thing I usually like to do is go over a case study of how people in industry are actually using this software. So I found this case study on the ECCO group, the ECHO group. They had a challenge, as I'm sure most of you have since you're here, to evaluate mold filling of plastic injection molded parts during their design to eliminate, their mold-related manufacturing issues and to enhance their lens optic performance and improve product aesthetics. And I should have mentioned this is actually a lens designing company who makes lenses for things like police cars, different types of vehicles, so all different types of lenses that convey lights made out of plastic. Mostly polycarbonate, I believe, or I would assume. So their solution, of course, implement SolidWorks Plastics professional simulation software. And we'll actually look at the results kind of at the end of this to see what implementing the SolidWorks Plastics software helped them achieve or helped them accomplish. So I have another poll question, trying to keep this a little interactive and see what's going on with your interest level. So what is your interest level? I'm going to go ahead and launch this one. Appreciate if everyone would answer that. So the choices were just checking it out to see what the capabilities are. I'm somewhat interested, but still have questions. I'm very interested, but wanted to see more in-depth show, more in-depth simulations, or I am ready to purchase this. So it looks like we have quite a few answers coming in here. Great, thank you. I appreciate the timely answering. Give it another second or two, and then I'm going to go ahead and close this out. And it looks like a vast majority are saying they are just checking it out to see capabilities, and then we have a small split between somewhat interested and very interested. So that's pretty cool. Great. Well, glad to see you guys are all here just to check it out. No problem. So what is SolidWorks Plastics? First off, it's an injection molding simulation software. Pretty self-explanatory, right? That's what we're using it for. That's what we're here to learn about. One of the huge benefits that I'm going to talk about more that I really enjoy with this software, and I think will benefit you guys if you end up using it, are it's fully integrated with SOLIDWORKS 3D CAD. So the changes that you make within the actual SOLIDWORKS model can super easily be parsed over to the simulation software. So there's really no exporting and importing like some other softwares where you would export a dumb geometry and then make a change and then have to bring that back into the software and re-simulate what's going on, rerun the simulations. So that's just makes it super value added with what we can do, and just really easy to really easy and quickly make changes. And I'll show you how to do that. So the next one, it's capable of predicting manufacturing related defects on parts and molds. So I'll also show you that and how easy it is to look at some defects that may happen in your injection molding, and then how you would go ahead and think about preventing those defects. So that's another way that it really comes in on the time cost savings aspect, and helps you guys ahead of time know what's going on without actually having to cut that steel and make those costly changes later. So who is it for? Well, it's for everyone basically, and I have this slide because I like to break it down into kind of the packages, and I'm going to talk about in the next slide, because the different packages include different aspects of the simulation software. So the first one that we kind of put it on there is the standard package, and that is kind of geared more towards part designers. The next one is the professional package, which is kind of more geared toward mold designers and mold makers, just because of what it offers. And then the premium package, geared more toward any advanced CAE analyst, or depending on what you're doing with your parts, just more complex simulations that are fully encompassing of everything in your model. And I'm going to talk about that in just a second, what I mean by that. So briefly, just showing you the packages of what we offer. Standard is pretty much what we're going to talk about today. We'll look at a few things in Pro. I don't have anything on premium here in this demo today, but standard, we just have filling. We talk mainly about looking at short shots, air traps, weld lines. Those are the kind of defects that we can easily look at. And then we can also look at multiple gates. Pro is where you kind of get more into your shrinkage and sink marks. If you're doing anything with co-injection or gas assist, great for that. Multi-cavity. It's also got some great runner balancing features. Cooling time if you're using inserts. And then of course premium is where you step into your, actually if you want to model the cooling lines and basically set up your mold material and look at a full-blown warp analysis of how your part's going to behave. As far as warpage goes, that's where you would need to step into the premium. So just depending on what your end goals are and what you're looking at, this is how the packages are laid out, and you can think about what you might need if you're interested as far as the packages go. So let's move on from that. So today, what are we going to look at? Got this brief visual roadmap here. I'm going to kind of try to keep this simple and just show you guys everything you need to know to kind of use the software on a basic level. But we're going to look at just a fill analysis. I have a part that is an iPhone case that I got and worked on that we're going to use as an example. So the end goal here is to optimize our wall thickness and our gate size. And then we want to check some other parameters. This is where the defects come in, like looking at our pressure, weld lines, air traps, things like that. Or if we're going to be able to fill the part, or we're going to have short shots, what are we going to need to do to make changes? And then in the end, we're going to select a best iteration from the choices that we have, right? So let's go ahead and jump into the software and take a look at what we got here. So the great thing about the SOLIDWORKS plastics is you can see that this is just a model within my CAD here. And I've got this iPhone 6 case that I modeled up. And what we have, let's switch it. You can see I have 4 different configurations in here. So if I switch the configuration between these, I already have the simulations run, of course. It asks me, do you want to reload the plastics projects? I'm going to say yes, because I'm switching I'm switching configurations. You have to reload the project every time you switch. So I have 4 done. We're going to look at 3 main ones here. I was kind of experimenting with one of the other ones. And then all I have to do to enable the plastics is just like anything else, go up to my add-ins, turn on my plastics, and of course I'm running the premium. And then this little icon with the arrows over the P will show up, and this is your plastics manager. And this is kind of how the tree looks in here and what you can do. So the first thing that you need to do to set up any of these analysis is just basically you just run down through this tree really simply. So if you're familiar with Sim or anything else, you can just run down the tree. So I set up a mesh here. You can right click, you can do auto or manual. It'll run you through some meshing steps. I'm not going to get too in depth with that, but you can see if I turn on my mesh, what my mesh looks like here. Actually, it looks pretty good. It could be a little better, but for time's sake, I wanted to keep it a little coarser. I could have made it a little finer so I could capture some of these corners a little better, but not a big deal for this because it's a simple part, and I pretty much know how everything's going to flow and behave. And then the next thing you can do, or the next thing you must do, is select a polymer. So I'm going to go through the things that you must do to make this work. So in this case, you can just right click here, say open database, and we have a vast material selection library in here. If you look at our default database, these are all the materials we offer with the manufacturers underneath. So if I were to expand something like a PC polycarbonate, you can see all the different manufacturers in here and all the different material types that we offer. So each one of these has its own chart of graphs, your thermal conductivity, your elastic modulus, your Poisson's ratio, your pressure volume temperature graphs, viscosity graph, specific heat, and then of course you have your material properties like where your melt temp and mold temp specifications are, your GT or your glass transition temperature, viscosity, Poisson's ratio, all that type of stuff is contained in here. Your max shear rate, shear stress. So really good information to have in here. In this case, for this part, you can see up here in the right top corner, I am just using a generic polycarbonate material, nothing special. I just picked a default generic PC. I knew I wanted this to be a polycarbonate in case I wanted to have some clarity properties for this case. Or if you decide you wanted to have it colored, we could overmold it with something and have a softer material on top to plug up some of these holes, right? So in this case, I'm not specifying a mold, but you can come in here, you can specify a mold size and mold material. I'm not doing that. And then the next thing I usually like to do is do my injection location. So if I pick my injection location, in this case, I just grabbed a center of the part as my first option, and I set my gate size and I hit add location and put that in there. So you can see in here, if I zoom in, I have my gate location right in the center of the part on the inside to keep it out of the customer's view, since the phone will sit in here, or away from their hands, so it's unseen by the consumer. So the next thing I did was I just looked at my fill settings and basically checked. This is mostly default. In this case, I just left the fill time locked down as 0.73 seconds, but you can unlock this and make a change here. And then this temp and mold temp, you could fiddle with this a little bit to see how everything's going to behave. I just left the defaults. I think this mold temp's a little bit high for this material, but that's what is specified. So I just left it as a default. And then I also left the injection pressure limit as default. One other cool thing we have in here is there's actually a machine. You can pick different machines in here. So you can come into this machine database and look at all these different machines in here. So if you already have a Sumitomo Systech 8040, 420, 800, D45, you can look at this and you can see say I want to know what my max injection pressure is, or my max injection rate, or my max shot weight. I can look at all that stuff. So in this case, I have an injection pressure limit of 23,211 PSI on this machine. So that's really great to know. So you can add those machines, or just look at them and see what the specs are on those machines. So in this case, this is the default SolidWorks machine. It's got 14,507 PSI of injection pressure limit. So I just left it as that. And you'll see in a bit why that might be an issue in this case. So the next thing I did, I just ran a flow analysis on this, and you can see the different types of analyses we can run: flow pack, flow and pack, pack and warp, and then we can do the whole setup, flow pack and warp. Now, of course, to do the warp, You really need to have your mold defined with the material. You need to have your cooling lines in there and all that type of stuff. So you can see in this case, I just have the part because I'm just running a simple flow analysis to see how this is going to behave, because I want to select a gate location properly, and I also want to select a part thickness properly in this case. So I'm going to go ahead and load my flow results. And in this case, this part itself is actually 1.5 millimeters wall thickness. What I really wanted to do was I wanted to get down to 1 millimeter or less, but you'll see what happened when I tried to accomplish this. And this is a good kind of real world example of what's going on here, right? So you can see my fill time is about 0.71 seconds here. That's what I'm looking at mainly. I'm looking at that. And I also want to know what my pressure at end of fill is. So you can see it's about 6,285 PSI. We can look at that fill time graph and actually run the animation on this, which is really cool. So it shows me how my part's actually filling and what it looks like as it fills. And you can see having the gate in the center on the inside actually gives me a very nice even flow throughout the entire part. There may be some issues depending on what you're trying to do or what concerns are. Like you can see if I look at these weld lines here, I may have a concern with the structural stability or the structural integrity of some of these weld lines being in these areas. So in this case, this one here, up here at this corner, could cause me an issue, or some of these other ones down here may also cause me issues. So I may just want to be aware of that. So I can easily just check these off and look at them very simply. Same with air traps. So I know, hey, I'm going to have some potential air traps in these areas where these little purple bubbles are. So I may want to add some venting in those areas. Now, of course, in this part, I'm probably going to have some venting here and around here. So, I mean, that's a given, but sometimes you might not know where you might need venting. So that's a really good thing to know. One other thing I like to look at in these is ease of fill. So in this case, for this example, since I'm using this 1.5 millimeter gate, you can see the part's all green. So there's not going to be any issues filling this part. Another really cool thing is the plastics advisor. So if I turn on this advisor, this comes up and it lets me know, gives me basically a synopsis. So if you are confused or don't know what you're looking at, you can easily look at every one of these and it'll tell you what each of these available results represents and what it's actually showing. And then it'll also tell you up front here what your status is. So in this case, you can see it's telling me, hey, you got a green light, because this part can be successfully filled with an injection pressure of 6,285 PSI, which is only 66% of the maximum pressure limit specified for this analysis, which means I am well under this limit. So that's good news, right? So I can fill this part. I know that I'm only using so much pressure from my max based on that machine that I specified. Another good one to look at is shear rate. Knowing that if you know the shear rate of the material, that might be a concern. PC is about 40,000 inverse seconds, 1 over second here. So in this case, it's only about 4,508, so no issue there. Another one, cooling time. In this case, we didn't really calculate a very good cooling time analysis, but it does give you a pretty good indication of what your cooling time might be, 6 seconds. So that's pretty good. Sink marks is another really good one to look at. So in this case, you can see I don't have any significant severe areas here, and my max sink mark is only 0.0024 inches. So I mean, that's pretty small. Nothing to really be too concerned about there. So we pretty much know based on that configuration where I have my gate that there's not going to be an issue, right? So let's switch back over to this thin wall part. So I want to actually decrease my wall size from 1.5 millimeters to 1 millimeter here. So in this case, I used all the same settings. I used the same mesh, so you can see my mesh, same mesh density. I used the same fill settings. I used the same material, this generic PC. I used the same injection location in the center of the part, and then I ran the flow. So let's take a look at what the flow analysis told me in this case, because I shrunk the material down to I shrunk the wall size down to a 1 millimeter from a 1.5. What am I trying to figure out from this, right? So my fill time is about the same. It's about 0.81 seconds, so within a few seconds of what the set point was. But what I really want to look at in this case is my pressure. So my pressure and my ease of fill in this case would be the first two things I would want to check out. So you can see my pressure is 14,110 in this case approximately. And if I pull up that advisor again, you'll see very quickly it's giving me a red light here. You can see right here right away, this is a great indicator, a great visual indicator of what you got going on. I have a red light here, and it's telling me this part can successfully be filled with an injection pressure of 14,107. Well, if you remember, my machine pressure was only about 14,000 something, or it was a little bit above 14,000. So it's telling me this is greater than 90% of your maximum injection pressure limit specified for this analysis. Well, we know that's not going to work because I don't even have a runner or a sprue on here, which is going to increase my pressure even more. So I know that there's no way I can be this close to my limit and still successfully fill this part or release this part for production or anything like that, right? And if I look at my ease of fill here, you can see that I've got some yellow and red spots on this part. So I know I'm in danger of not filling these areas or having a hard time filling these areas since I'm very close to my high pressure limit. So there's really no point in looking at anything else on here as far as what we have going on and defects or anything, because I know I'm not going to be able to fill this part with a 1 millimeter wall thickness, right? So I'm going to go ahead and check out of that. So let's flip back over to another option was I wanted to try this end gated option. So instead of having the gate in the center, I was thinking in this case that the design may include a like a rubberized outer coating that would slip on like you see a lot of cases have. So I actually put the gate at the end here, thinking, hey, if I'm going to put a rubberized coating on this, it's not going to matter if I end gate this anyways, right? So I thought that might be easier for automatic degating and depending on how many cavities I want to have in this mold. So you can see the difference in the flow pattern or the fill pattern here. Instead of from the center and evenly filling out, now I have this really long flow length though, which is a good chance that might hurt me in the end as far as that gate location. Because if you remember before, I had it in the center, which pretty much gave me a relatively even flow length throughout the part. Now I have a really long flow length, which I'm not too keen on designing around. So the first thing I'll look at here, same thing. My fill time, about the same, 0.73 seconds. My pressure, 12,000 though. So if I look at my advisor, another great example of this advisor, which I kind of like. Don't really need it too much for the explanation of what I'm looking at, but I do like that it gives you an automatic, very quick indication. It gives me a yellow light in this case because I'm using 12,000 PSI of my max 14, which is saying it's greater than 50 but less than 90, but still not a great range. It's within a reasonable range, 82.79% of your maximum. That's not really very reasonable. I probably would never design like this just because that's way too close to the max to be safe. So yeah, this part, even though it's still the 1.5 millimeter wall thickness, because I have such a long flow length, it increased my pressure almost twofold. So in this case, I wouldn't even look at this part as far as a viable option for that gate location, right? So I would just check out of that and say, I'm not going to use that part, right? Or I'm not going to use that gate location. So in this case, the default was probably the best, which was the center gated option with the 1.5 millimeter wall. But I really, really wanted to have that 1 millimeter wall thickness or less. So in this case, let's look at a summary here. If I jump back into PowerPoint, kind of a summary of my iterations here. So I use generic PC. I'm calling it a pin gate. I'm probably going to have 1 to 2 parts per mold. I really wanted to have that 1 millimeter. I put desired wall thickness was 1 millimeter. But you can see my injection pressure limit that I specified was only 14,507. And then I have my mold and melt temp here. So iteration 1, I had a 1.5 millimeter wall and I had a 1.2 millimeter gate. I kept the gate the same, the gate diameter the same throughout. So it's a 1.2 millimeter gate. I used inside center, and then the last one we looked at was the end of part, right? And then you can see my injection pressure changes here. So with the 6,000, I'm good. I can fill it. I have a cooling time of approximately 6 seconds. I don't see any issue with that, but I didn't meet my specifications for the 1.5 millimeter wall. The second one, I almost blew through my injection pressure limit max with 14,000, so that's as no good on the fill. Ease of fill is very poor. And then the last one, I changed it back to a 1.5 millimeter wall, but I end gated it, and that bumped me up almost twofold from my original to 12,000. So I put ease of fill 1 is okay, but not great. I wouldn't do that. I definitely wouldn't use that part just because of the gate location, long flow length. So how am I going to get to a 1 millimeter wall on this part? Basically, I'm going to have to get another machine, or I'm going to have to somehow figure out if I can use a different machine with a higher injection pressure limit and then rerun it. So I would go into my machine database, figure out, can I use this machine with, say, 25,000 PSI or 30,000 PSI on my injection pressure max? And then, if I have 14,000 PSI for a 1 millimeter wall with that center gate, and I'm only 50% of my max if I use a 30,000 PSI machine. So I could definitely do that. So that's the option there that you have. So basically what I'm looking at in plastics is telling me what my pressures are and that where I'm going to be able, how thin I can thin this part up to actually and still actually fill it safely, and what machine I'm going to have to use. So depending on what options you have there, that's definitely some good information to have when you're trying to design a part, right? So some benefits of what we looked at. We were able to predict and avoid manufacturing defects like short shots, weld lines, sinks, and if you're going to be able to fill the part, basically. What's this going to allow you to do is eliminate costly mold rework. So it's good to know that beforehand, right? If I design this 1 millimeter wall and I put it out there and it doesn't fill, then I'm going to have to either do some rework and get a 1.5 millimeter wall or even larger, or I'm going to have to switch to a different machine with a higher injection pressure limit. This allows you to decrease that time to market significantly, less mold iterations, less changes, improve that part quality. So I know I'm going to be able to fill that part with a 1.5 millimeter wall without issue. If for some reason I decide to go with the 1.5 mil or the 1.5 millimeter wall with the end gate, there's a good chance I'm going to have trouble filling that part. So improving part quality. And the great thing about all this is it's integrated with 3D CAD, so you can see me switching between the configurations very quickly. The changes I made to that part were very simply. You can control the wall thickness if you set it up with just a shell, so changing one dimension. So very easily changing and setting that up back and forth. I don't have to import and export parts out. I absolutely love that. So this slide is great because it shows the cost of change and how SolidWorks Plastics is really going to benefit you. So, everyone knows if you make design changes early on in the product development phase, it's going to cost less, and it also has the greatest impact later on down the line. The cost of change is going to increase substantially further downstream in the process, so that leads to delays. So you can see in the chart there the impact of change and the cost of change. So the impact of change is highest at the beginning of the process, and then the cost of change is highest at the end. So when you make changes when you're toward the end, it's a very costly, very delay-ridden process. So that case study we talked about with the Echo Group, right? What were the results that they actually saw from implementing SolidWorks Plastics? So they were able to minimize their iterations with the mold maker, which is a great, huge benefit. Only doing 1 to 2 possibly iterations. Eliminate mold-related production issues. So all those defects that we were able to look at in SolidWorks Plastics, like the sink marks, being able to fill the part, weld line locations, that type of stuff. In this case, I read that they had a very critical weld line issue that had a negative issue on the refraction of their light through one of their lenses. So they were able to actually move their gate so they could change that weld line location, and they were able to simulate all this before they actually molded any parts. So think about how changing that gate location after they already began molding how costly that would be, and what they were able to save just by implementing with SolidWorks Plastics. They optimized their parts for stiffness and how the mold filled. Another great thing. So they added some ribs to parts in certain areas, and they needed to see how those would fill, so they were able to use plastics to simulate that. And then they improved their lens optics and product aesthetics. So that was basically what I had said about moving the weld lines around and changing up the refraction on the light. Improved design visualization and communication. So how the part's actually going to look and how it's actually going to fill. Able to see that in real time with those animations, a great feature. So the goals that we talked about at the beginning. Did we actually meet those goals? Set up a study. Yes, we did. I felt like we set up a study. Did we analyze injection molded parts for defects? Yes, we looked at a few iterations of the same part. We looked at the defects. Cool. We used configurations to evaluate our design. So I had 3 configurations I showed. We looked at those to check our designs and see how everything would work and what we can and can't do based on the machine sizes we have. We made critical design changes to reduce molding issues. So our wall thickness and where our gate was, critical design changes we needed to figure out before we actually cut steel. We did that too. So it looks like we've met all our goals for this webinar. That's great. So that concludes that section. Some upcoming content I wanted to remind everyone about. Don't forget to join us this month. We have the details about 2D drawings. Webinar next week, 2 p.m. on Tuesday. So that's the second part of our 20-minute learning series about about drawings this time. And I'll be hosting that one. So I'd love to have you guys back. And then the next one we have is next Wednesday, 5/25, CAD renderings and animations. So that's going to be on our new Visualize product. So I want to thank you guys for attending and just, what did you see today that could benefit your company? And then remind you to think about how our products can help you with your upcoming projects and what you have going on there. So if you guys are using any plastic stuff, feel free to reach out to me or anyone at DDI for any plastics information. I would definitely be the plastics contact. I could help you out. Once again, my email, jspaniel@ddicad.com, and my phone number's down there on the bottom of the screen. And don't forget to follow us on Twitter, Facebook, and LinkedIn. So we're on Twitter at DDICAD, and then Facebook and LinkedIn, we're Digital Dimensions Inc. So that pretty much concludes the webinar. I'll stick around for a few minutes if you guys have any questions or anything. Other than that, you can go ahead and email me or call me, and I'll definitely be more than happy to help you out. So thanks for attending. Have a great afternoon.